And so we had this last time. It'll probably be good for you if you hear it again, right? So we ended the lecture by defining this operator, the product of the velocity vector, the dot product with the velocity vector with the gradient operator. So when you do that, let's repeat it right here. Let me cover most of it so you don't get all confused. That's just the same quantity. You do the dot product, you get u times ddx plus v times ddy plus w times ddz. And this is our differential operator. So v dot del is a differential operator which is represented by this quantity. So what we did is that we know is, first of all, it is a scalar operator because the I, j, and k are gone, right? Because of the dot product. So this is a scalar operator. It's different from the gradient itself that we were just talking about. The gradient itself is a vector operator, but when you make the product of v dot del, you come up with this new operator called a scalar operator. So you can apply an operator, like I was just saying, to any field. So if I choose to apply this scalar operator to the velocity, so apply this operator here to the velocity field, we get that, right? So all I'm doing is applying this to the velocity, and that's what is meant by this notation. So this is not the product of v dot del times v, is v dot del applied to v. And we agree that we would get this because all I have to do is look at my operator and apply the derivatives to my function, in this case it's a v. And as I say here, this is the convective acceleration. So that term is part of the acceleration of a fluid element. It's not all of the acceleration of the fluid element, it's just part of it. What's missing to get the total acceleration? We're missing the local acceleration. So if we go back to what we had last time, here is the total acceleration at the top in that box. This term that I just showed you, which you don't see anymore on the screen, but is this term, this last term. So when I look at the total acceleration, I have two terms. I have the partial v partial t, which we defined last time is the local acceleration, partial v partial t, and then we have v dot del applied to v, which is the convective acceleration. So when you think of a fluid element that is moving about, you think of its acceleration, it has those two parts. It has what we call local acceleration and what we call convective acceleration. And both together make up the actual acceleration of the fluid element, right? So, and we also said last time, and I repeat it here, that what we know as steady flow means that the local acceleration would be 0. Because that's the meaning of steady flow. There is no local variation with time. And it should be very obvious to you that even though a flow is steady and there is no local acceleration, a fluid element can still have acceleration because it will still have the convective acceleration, right? So, so going back to this one, the very bottom of it, our convective acceleration, which I have written here as u partial v partial x v partial y plus w partial v partial z. You have to remember that this is now a vector because the acceleration is a vector. So both the local acceleration and the convective acceleration have to be vectors. And this vector would then have three components. This vector would have three components. And we saw those components last time when we wrote the full expression for the acceleration, and it is right here in the red box. Those are now the three components of the acceleration. So the first three terms in each of the components come from the convective, from that compact term. So u du dx plus v du dy plus w du dz. That's the convective acceleration in the x direction. And then you add to it the local acceleration in the x direction, and that's your component of the acceleration in x. And then similarly, you have a component in y and a component in z. So that big monster, total of 12 terms, make up the acceleration of a fluid element. It is actually a very important concept in fluid mechanics, and we won't really get too deep into this at this point. But if you think of this as terms in a differential equation, what is significant about these terms, the convective ones, so the 9 on the left, is that they are nonlinear. They are nonlinear terms. Why did I say that they are nonlinear? Suppose that I don't know the velocity field. I'm trying to determine the velocity field, in fact, by solving the equations. I don't know the velocity field. So I want to find out what u, v, and w are, so I know what the velocity field is. And this will appear in my Newton's second law, right? It will appear in my equation that governs the motion of the fluid. Why do we say that these are nonlinear terms? These 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Why are they nonlinear? What makes them nonlinear in a mathematical sense? Where are my math experts? Why is that nonlinear? Just look at one of them, the first one, u du dx. Why is that nonlinear? Because it's multiplying the unknown, which is u, with the derivative of the unknown, which is du dx. Right? And in differential equations, that is a nonlinear term. Anytime you have the product of the function times its derivatives, or any combination of products, anytime you see a product of the unknowns, that makes a term nonlinear. So these are all nonlinear. That makes the solution of the equations very complicated and very interesting. Okay, but enough of this. Let's look at a very simple example. And this example is in the text. It might be in the homework. I don't recall, but we are told that, this is problem 431, that there is a diffuser which you know is a device to reduce the velocity, to reduce the speed of a flow. So there's a diffuser, flow is going out, and we are told what the velocity is. So this is a very straightforward example just to see how to obtain the acceleration. And this is such a simple example that the velocity field is given to us, and it's fairly simple. It's just given by that expression right there. We're told that the velocity has only one component in the x direction, and this is what that component is. So this quantity here on the right-hand side before the unit vector I is our lowercase u. There is no velocity in the j direction across perpendicular to the axis of the diffuser, and there is no velocity normal to the paper. All there is that. But it is time dependent. There is a time there, and of course it depends also on x. And so the question is very simple. So here's the three components. U is what was given to us, v and w are 0. What is the acceleration? So what can we say about this flow? Is this flow steady or unsteady? What do you think?
Unsteady.
Unsteady, right? Is it one-dimensional, two-dimensional, or three-dimensional? This is one-dimensional. There is only one component of velocity. So it's 1D and it's unsteady. And therefore, when we look at our big expression for the acceleration, let me go back and show it to you one more time. When you look at this in the box, since there is no V and there is no W, there will be no acceleration in the y direction. There will be no acceleration in the z direction because there is a V there, a V there, a V there, and a V there. Those are all 0. And the W is all 0. So all there is this. And in fact, if I look at these 4 terms, only 2 will survive, which are first and last. Because the u velocity as given to me doesn't change with y, and it doesn't change with z. But I know it does change with t and x. So when I write my acceleration, all I have is those 2 components. The du dt, which I calculated here. The local acceleration would be partial u, partial t, simply differentiating that in time. And then the convective acceleration, which again is only one term, and it will be the product of u times du dx. So again, now this is just a substitution of u times du dx. You put it all in there, and you get that. Negative v naught square over L times that parenthesis times that second parenthesis. That's my convective acceleration. It's all in the I direction. So my total acceleration, when I put it all together, is the one that you see there. That's the total acceleration. And as you can see, it is unsteady. The unsteadiness is still present in the acceleration. There's a time dependence there and a time dependence there. And there is a dependence with x. What happens after a very long time? What happens after a very long time? It should become 0. Right? The acceleration becomes 0 after a very long time. Yes?
So if there's any time dependence, it's automatically unsteady?
I'm sorry, say that again?
Were you saying that if there's any dependence, it's automatically stays unsteady?
If there is a time dependence in your equations, velocity or acceleration, then it is unsteady. So let's be careful here. What happens after a very long time? This goes to 0, right? This goes to 0, but this doesn't, right? So I said first that the acceleration goes to 0, but after a very long time, it doesn't go to 0, but what happens? After a very long time, it becomes steady. That's the correct answer, right? It becomes steady because the exponential terms disappear, but I still have this term. So after a very long time, it becomes steady, but there is still an acceleration. Look at the velocity. If I slide this down so we can see the velocity again there at the top, right there. Right? What happens with the velocity after a very long time? It also becomes steady. After a very long time, this goes to 0, but the velocity becomes then, after a very long time becomes steady, and it's just v naught times 1 minus x over L. So the velocity is still decreasing as I go downstream. If I go downstream, because this quantity would get larger. So there is still an acceleration. The flow is actually a deceleration. Right? The flow is slowing down as it moves from left to right. That's a very simple example of how to calculate the acceleration if you have the velocity field. And of course, it's very simple because most of the acceleration terms were 0. Any questions about this example or the acceleration?
What's the x and the L stand for?
Well, the x is just the horizontal coordinate, so you could put it here. Where's my drawing? You could measure x from here, for example, from some origin, right? And L is some length, right? The problem doesn't specify what it is, but presumably it will be some length. I wouldn't say it's the length of the diffuser, because if that were the case, then the fluid completely stops. So L would probably be some length, but it's larger than the length of the diffuser, assuming that maybe the velocity expands out and eventually stops. But within the diffuser, it couldn't stop. Yeah.
So did you say that equation for the velocity was given?
Yes.
Okay.
This was given to make our life easy. So velocity is given, just compute the acceleration. Any other questions? All right, so let's switch gears here and talk about something that should be familiar from thermal. What we're going to do in the next chapter, which will be after the midterm, will be to look at the solution of fluid mechanics problems using what we call the control volume approach. And you know what a control volume is from thermal. And thus the control volume approach simply means that we're going to be looking at flow problems, fluid mechanics problems, in which perhaps we can treat the entire region where the flow is occurring. Maybe it is a turbine, maybe it is a compressor, maybe it is a pump, in such a way that we can define a control volume. And we need to look at fluid going into the control volume and fluid going out of the control volume, and then apply our conservation laws, conservation of mass and Newton's second law, to that control volume to get some quantities that we might be interested in getting. So do you remember from thermal, a control volume is right there. If I define it with the contents inside the dashed line, that would be my control volume. And what makes it different from a system, a closed system, would be that for the control volume, we would allow for the mass to cross the boundary. So that's the simplest example. Some mass coming in at some rate, m dot in, some mass coming out. Now, we usually have slightly different terminology in fluids than what we have in thermal. In thermal, we always talk about open system and closed system. And a closed system in thermal is what sometimes, most of the time, we refer to in fluids as a controlled mass, since the mass doesn't change. So it's the same thing, a closed system or a controlled mass. Now, in fluids, sometimes we just say system. So in fluids, when we say system, many times we mean closed. So when you hear the word system within the context of fluid mechanics, is a closed system. Whereas what we used to call open system in thermal is what we call in fluid mechanics a control volume. So one that allows for mass to cross the boundary. So just a simple, a slight change in the way we refer to quantities. But let's say that we have such a thermodynamic control volume. Again, there is the schematic. I could write a very simple equation for conservation of mass. So I know that if I compute the rate at which mass is changing inside this control volume, so inside the black dash line, from mass conservation, it's almost intuitive that the rate at which the mass changes inside the control volume has to be equal to the difference between the rates at which mass is coming in and mass is coming out. That's, like I said, by this time, it should be fairly intuitive that that's the case. So if I just, and that would be an equation for conservation of mass, that simple equation. Now, if I think of a system, I know that. Because remember, a system is a closed system for us. So this is the difference between these two quantities. The one on top in this equation, the mdt, is for a control volume, and that would be the rate, the difference in the rates of influx and outflux of mass. But if I had a system, nothing crossing, then the change of mass for that system in time would have to be 0. But now let's try to make this concept a little bit more general. Rather than be a calculation of mass conservation, let's say that we're writing for any other property. Instead of just mass, suppose that I have another thermodynamical property that is capital B, an extensive property. To give you an example, this could be energy. B could be energy, but it could be any other extensive property. And we know from thermo that I could write an intensive equivalent. So if B is a certain property like energy, then capital B that is, then lowercase b would be energy per unit mass. So I can always write that relationship between the capital property and the lowercase property. So what we want to do is discuss something that we call the Reynolds transport theorem. And I'm going to start by showing you a simple Reynolds transport theorem. And then we're going to build up and make it a little bit more complicated. So here it is. I will state that a simple Reynolds transport theorem would tell me that the rate at which that property B changes per unit time for the system has to be equal to the rate at which that same property changes for the control volume plus the flow of property B per unit time out of the control volume minus the flow of property B per time into the control volume. Why do I say that? Well, very simple. Go back to this equation that we had earlier for the mass. That was the mass conservation equation. So what I did is I just moved all the terms to the left-hand side in the equation that we had before. For mass conservation, I just put the m dot in on the left with a negative sign and m dot out to the right with a positive sign. This is equal to 0, so it shouldn't be very hard for you to see that, in fact, that's because if I write it this way, I am writing an equation for the time variation of the mass for the system. In terms of a schematic, if we go back to this drawing, right, all I'm saying is that when I write it the other way, I am looking at a closed system. So if I look, for example, if my closed system is all the mass that was inside the control volume initially, then sometime later, some of my mass comes out, but I have to keep it into my system. That's why I draw a new dashed line inside the old one that actually includes the mass that went out because that was part of my system. And then, of course, I would have to subtract this mass that comes in because that was outside of my system. And therefore, when you move these terms to the left-hand side and write the equation that I wrote here, really what you're saying is that you're writing an equation for the total variation of mass per unit time for the system. So if I extend that then to my property B instead of M, all I have to do is just replace the M with a B in my equations. So these are exactly the same equations, but now I have written a B instead of an M, out, in. Out is positive, in is negative. And then the other term is the same. D dt, but now it's d dt of B instead of M. The only other thing that I did here, it was just to remind you the use of this capital D. This is not the differential operator that we were talking about a moment ago. It was, remember, the way to remind ourselves that that's a derivative following the fluid. So whether you write it with a straight D or with a capital D doesn't really matter too much as long as you know what you're talking about. So, but it's the system in both cases. So that is then this equation right here is my simple Reynolds transport theorem. It tracks down the variation of property B in a system by keeping track of what's happening in the control volume and what's flowing in and out. Now, how can I write these flow rates, capital B dot, out and in terms of the lowercase b, in terms of the property B per unit mass. Would you agree with me that it would have to be like that? Move that up. B dot in is lowercase b in times m dot in. Because if you work out the units, you get what you want, right? Again, for example, if you think that B is energy, then capital B dot is energy per unit time. Lowercase b is energy per unit mass. You multiply time mass per unit time, which is m dot, you get energy per unit time. So I have a simple way of expressing the flow of the capital property B in terms of the intensive property lowercase b. What I did on the right-hand side is something that you will recall, right? We have a simple way of calculating the mass flow rate through an area by multiplying the density times the velocity times the area. We did that a while back. So if I do that for both, for B dot in and B dot out, then I have my simple Reynolds transport theorem. Move that up. Written there. Sorry, when I wrote it first, I wrote in where it was out and then out where it was in, so I had to cross it out. So the change of property B per unit time for a system is the change in that property per unit time for the control volume, plus the two terms that represent the flow out and the flow in. Out is positive, in is negative in terms of lowercase b. So this is a simple Reynolds transport theorem. And you say, wow, you know, this seems so abstract. It'll be obvious what the practicality is when we look at examples, but that's how it comes about. It is a simple one. Let me see if I have time to, I guess I do, to show you now a more comprehensive Reynolds transport theorem. If you thought this was difficult, wait until you see the more comprehensive one. But it only has to do with the way we calculate these terms, the time variation in the control volume and the fluxes. Because, remember, these terms, for example, on the right-hand side, make an assumption. When I say that I can compute the mass flow rate as the product of rho v times an area, right? And suppose that this is the area that the substance is flowing through. That is the area. Right? What assumption is going into that expression?
Incompressible?
No. It has to do with uniformity, actually. Let's think about that this is the end of a pipe, for example. Right? Let's try to make a more realistic schematic of what's going on at the end of a pipe. So here, this is what's a sort of a generic schematic, and I'm going to make a better one. If I'm going to draw the velocity, how should I draw it?
It'll be greater in the center and less out of the edges.
Greater in the center and less on the edges. Very good. So it'll be something like this. In fact, it'll be 0 at the edges, and then it should get larger, larger, larger. The largest value is at the center, and then less, less, less. So in fact, it'll have some shape like that, if I make a realistic drawing. So when I say that the mass flow rate is rho VA, the question arises, what's that V? That would be a good answer, the average. What if the density varies also? What if the density of this fluid happens to vary on that section as it flows out? What is that density? Again, you could say an average. So if you say, well, this is some average density and this is some average velocity, then that's okay. But suppose I say, no, we really need a very precise calculation. I want you to compute the mass flow rate here very accurately. how would you do it? How would you do instead of rho VA? Say that again? You could divide it into sections, and then that's taking you in the right direction. And I said, do it very precisely. Integrate over the sections that he's talking about. You would divide it into sections, and those sections that he's talking about would be differential areas. Right? So I would just look at differential areas, and then all I have to do is take the density on that section, take the velocity on that section, and then, of course, integrate the whole thing over the area. And that would be a very accurate way of computing the mass flow rate. So you see how we went from the very simple expression to one that is a little bit more accurate by doing an integral. Because if you take the density and the velocity as constants, you would take them out of the integral sign and you go back to the previous equation. So there is one way in which one component of the Reynolds transport theorem becomes more general. And suppose I make it even more complicated. Suppose that I tell you, well, actually what happens is that, again, here is the area, but the velocity not only is not the same everywhere, or the density is not the same everywhere, but it turns out that actually the velocity doesn't come perpendicular to the face, to the area. It comes at an angle. Suppose I say that, and so if here was the axis, there is an angle there. What do you need to change in this expression? If I now tell you that there is an angle also involved. You have to multiply the velocity by a cosine theta. So you have to say, whoops, I have to do m dot is integral over the area, rho, if that's one of the sections that we were talking about. It's not v, but it's actually v cosine theta dA. That's the mass flow rate. All right. So if you look at then, say for example, that term, which is not the mass flow rate, the B rho VA, is the mass flow rate times property B, and you want to do the same thing for this term. Remember, that term was the B, capital B, dot out. It's now going to be an integral. Just repeating everything we did. The only difference is that we have to stick in the value of B at that particular spot. So I would say B rho V cosine theta dA, integral over the area. And I would have to do the same thing for capital B dot in. Now, there is another way to write this that is a lot more elegant. This so-called V cosine theta that you have seen before, I'm sure. What you do is on each point on the surface, you define a unit normal vector n. So that little n vector is a unit vector that is always perpendicular to the area. And instead of writing V cosine theta, what can I write? Very good. Integral area B rho V now as a vector dot n dA. All right? And that's the V dot out. I'm sorry, that's the capital B dot out. Now it turns out that I can include the other one, the B dot in the same expression, because V dot n will be positive when the angle is less than 90 degrees. But if the angle is more than 90 degrees, V dot n will be a negative number. And therefore, it will be the flow going in. So in fact, this is not just B dot out. Once you put it like that, this is B dot out minus B dot in. So you have both terms in one. So I can now go back, and I'll probably end it here because we won't have time to go over the rest, and rewrite my not so simple Reynolds transport theorem as dB dt for the system is equal to partial B partial T for the control volume. We haven't touched the left-hand side. And remember, the next terms were plus B dot out minus B dot in, but I have now those in just one quantity, which is this integral. So there you have a little bit more sophisticated Reynolds transport theorem. Question? Why I've added the minus B dot in? Because the product of the velocity dot n will give me the correct sign. If it's going out, it'll be positive. If that product is negative, it'll be coming in. So by doing an integral, I'm taking into account whatever mass is going out and whatever mass is going in. Okay, so we'll meet on Wednesday.